Here in this video, we're going to look at what we call upper and lower sums, and we're going to use this to find the area underneath a curve. If you look at this middle graph here, we want to find the area of this shaded region. Well, there's no geometry formula that we have that we can find this area that's underneath the curve. So we're going to estimate this area. First, if we look on the left here, we can draw a bunch of tiny little rectangles underneath the curve, and if we find the area of each rectangle by taking the length times the width, and then we could sum up all of the rectangles, and that would give us an approximation to the area. And clearly there's a little space left here, so therefore this area would be less than the area of the actual region. And then we're going to look at drawing rectangles that go slightly above the curve here, your circumscribed rectangles, and clearly this area, because our rectangles are going above, are going to be slightly greater than the actual area. So let's look at an example how we can do this. And the first one we want to look at is how can we find the area using these inscribed rectangles. Now, for example, here this says we want to find the area of the region below the curve on the interval from 0 to 2 using lower sums with 5 rectangles. So here's our function, f of x equals negative x squared plus 5. So they want us to use 5 rectangles to estimate the area that's underneath this curve on the interval from 0 to 2. So first of all, we need to calculate what is going to be the width of each rectangle. We want the width of each rectangle to be the same, so we need to take the total length divided by the number of rectangles that we want. So in this case, if our interval is from 0 to 2, we could simply take 2 minus 0 divided by the number of rectangles. So therefore, we're going to use a width of 2/5. So we need to mark off each rectangle on the axis here. So if we start with 0, we're going to add 2/5, and then we would get 4/5, 6/5, 8/5, and then of course we would end up here with 10/5, which would be equal to 2. So now we have our markings for our rectangles. So in other words, we're going to start and we would have first rectangle would go from 0 to 2/5. Our second one would go from 2/5 to 4/5, and so on. So I'm going to mark off each of our rectangles. All right, so here we have the left and right endpoints of our rectangle. Now, because we're looking at the lower sums, we're looking at drawing our rectangles below the curve. So with this problem, if you notice, if we were to draw up from 0 and over, we're going to go above. But if I start from 2/5, and if I go up and then over to the 0, so therefore notice our rectangle is below our curve, and then we go up at 4/5, and then at 6/5, and then at 8/5, and at 2. So you'll notice that our area here is going to be a little bit less because we're missing this part here. So the question is, if we look at this closely, notice we're going to calculate the area of each rectangle. So if we look at the first rectangle here, goes from 0 to 2/5, so we know that the width is 2/5. So if we're looking at the area, we could simply say the area is going to be equal to the width of 2/5, and then we need to find the length of the first rectangle. So here we have rectangle number 1. Now, do we want to use the left side of the rectangle at 0, or do we want to use the right side? And you're probably thinking, does it really matter? Well, for this problem, notice the only way we can find the length, which we'll call this L1 for this first rectangle, is if we go all the way up. Notice the right side of the rectangle, and this is the important part to understand. The right side of this rectangle, when it goes up, it touches the graph at this point here. The left side doesn't touch the graph. So we know we can find L1 because that's just simply what? That's simply going to be the y value evaluated at 2/5. So if you go up to the graph, we could go over to find the y value. Or in other words, we can take 2/5 and plug it into the function above, negative x squared plus 5, and that will give us L1. So we need to take 2/5 times L1 plus 2/5 multiplied by L2. Well, that's going to be our second length here. And again, notice this right endpoint of 2/5 touches the graph. And then we would have 2/5 times L2 plus 2/5 times L3. And notice that's going to touch the top of the graph here. Plus 2/5 times L4. And notice here again, this point touches the graph here, so we use the right. So that's 2/5 times L4 plus 2/5 times L5. So if you notice, we're using the right side of our rectangles to calculate the length. Now, to make things a little bit easier, notice here each one of these is multiplied by 2/5. So we could simplify this by simply factoring out the 2/5 so that we do not have to write this over and over. So we would simply have L1 plus L2 plus L3 plus L4 and plus L5. So that way we don't have to multiply the 2/5. We can just do that at one time at the end. So now, how do we actually find this L1? Well, L1, again, we're looking at the 2/5. So we're simply going to plug that 2/5, like I said before, into the original function negative x squared plus 5. So we want to evaluate 2/5. We want to evaluate the function at 2/5, and then we want to do the same thing for L2, except for here, this is going to be evaluated at 4/5, and then for L4, whoops, skipped L3. For L3, we're going to use 6/5, and then for L4, we have 8/5, and L5, f of 2. So now this is the part we don't want to forget. We want to take actually each one of these. Now, of course, this means your function f is evaluated at 2/5. So we're going to plug that into this function here. So if we're going to do that here, we would end up with our 2/5 out front, and then f of 2/5. If you plug 2/5 into this function, you're going to get, and keep in mind this would be negative 2/5 squared, so you don't want to square the negative, so it's negative 2/5 squared plus 5. So you're squaring the 2/5, then the negative, and you're going to end up with approximately 4.84. And then we're going to take 4/5 and plug that in for x, and we'll get 4.36. And the same thing for 6/5, and we get 3.56. And if you plug 8/5 into the function, we get 2.44. And if we plug in 2, clearly you're going to get 4, so it's a negative 4 plus 5, so that would simply be plus 1. Now keep in mind, these values here, 4.84, 4.36, 3.56, 2.44, and 1, that's given us the length here of each of the rectangles, L1, L2, L3, L4, and L5. And that's because if we plug 4/5 into the function, that's going to take us all the way up here to this red dot, which is giving us the height of the rectangle because it touches the graph at that point. And if we perform all the calculations here, you're going to end up with an answer of 6.48. And keep in mind, this is the area that we've come up with, and we know this is going to actually be slightly less than the region that we're looking for. And that's why we call this the lower sum, because it's giving us the lower sum, or this smaller area for the region. All right, now quickly I want to look at how could we use this sigma notation that we talked about before for summation. Well, we could set this up as the area equals our sum of I equals, well, where we're going to start at? Well, we're going to use 5 rectangles because we want to keep in mind we want to sum up all 5 of these rectangles here. So we're going to start at 1 and we're going to go to 5. Now, we know the width, just like I factored out over here, our width is always going to be 2/5. So we know that we're going to have 2/5, and now we need to figure out how can we calculate the height. Well, we're going to take and plug 2/5 for the first one. We plug 2/5 into the function, our first L1. So we could think of f of 2/5. Now, if we plug that into the function, that's going to give us the first one. So if we were to plug in, let's say, f of 2/5 I, and let's see what happens here. If we plug 1 in for I, we get f of 2/5. And notice over here, that's what we want, right here. Well, then the next one, we want f of 4/5. So when we go from I equals 1 to I equals 2, we'll plug a 2 in for I. You're going to get 2 times 2, which is 4/5. So that gives us the f of 4/5. And then we want 6/5. Well, when we go from 1 to 2 to 3, plug 3 in for I, you get 6/5. And if we plug 4 in for I, we get the 8/5. So it's f of 8/5. And if we plug in the 5, we get 10/5, which is the f of 2. So this formula here, the 2/5 is giving us the width, and the function evaluated at 2/5 I, this is going to give us the length of each rectangle. So we want to sum all of these up, and that will give you the area. So for example, we could rewrite this as the sum of I equals 1 to 5. Now the 2/5, you have a couple options. We can leave the 2/5 here, and then we could simply evaluate our function here. Now at this point, we want to take this whole 2/5 I and substitute this in for the x. Okay, so be careful. So we would have minus 2/5 I, and that whole quantity, because of the function here, is squared, plus 5. Okay, so now, just like we did in the earlier section here, early on in the other videos, we can use your calculator to plug this summation and evaluate this using the calculator. Now keep in mind here the 2/5 here, because this is a constant. If you wanted to, you could actually take this 2/5 and we could just move that out front so that you would end up with the sum of I equals 1 to 5, and the 2/5 is out front. And then on the calculator, you could just simply type in this minus 2/5 I squared plus 5. And once again, you should end up with the same answer of 6.48. Now, this may be a little bit better than the answer up here, but these should be very close depending on how much you rounded your answers up here above. So once again, what have we done here? We have calculated an approximation to the area that's under this curve on the interval from 0 to 2. And again, because we were below here, our rectangles were below, this is called the lower sum.